Well, good morning, everyone, and welcome to physics class. And I know you already read this chapter, and so I'm not going to take a long time going over it, but I do want to review it and then go over the homework questions. Um, I decided to assign it to you to just read it. Thought you could handle it. I do want to talk about the math and the latter part of it a little bit more. Anyway, and I'll just comment. I was able to get some PowerPoints from Bob Jones, but I had to adapt them because they had a few issues. But some of the decorative parts of this is actually borrowed from Bob Jones, which is kind of nice for me. Okay, so let's talk about electrodynamics. We're going to do electricity and magnetism. Electrodynamics is moving electricity. We talked in a previous chapter about static electricity. This is moving electricity, and or sometimes called current electricity. So this is a very up-to-date subject because it's current electricity. And this first section A that you read parts of cover current, voltage, and resistance. So let's start with what current is. Section 20.1, if you're following along in your book. Symbol for current is I, and I had to change the font there to get the so it looks more like an I, but it's still a little weird. The symbol for current is I. I have no idea why. I'm not sure how I connects to current, but it's defined as a continuous flow of charge. Now, in static electricity, we did have flows of charges, but they weren't continuous. They just were boom, like lightning or electric shock when you touch the wall plate and you get a shock. That there's flow there, but it's brief and it's not repeated. This current is a continuous flow of charge. And so electrodynamics is the study of the causes and effects of current electricity. Now, the motion of electrons creates a current in metals. This is typically what we're dealing with solids. You have metals, you have free electrons. If you remember from physical science and chemistry, we talked about metallic bonding. And in metallic bonding, there's an electron C, and there are free electrons or delocalized electrons. Those are what are moving. Those are what are free to move in a metal. Now, electrical conduction in metals begins with a potential difference in the metal. Now, potential difference, I find a kind of abstract concept when we talk about electricity, but if you think of the parallel to potential difference is fairly straightforward. This is the same idea as a ball dropping from a high place to a low place. There's a difference in the potential energy. This is a little different, but it's the same concept. It's a parallel concept. Potential difference. There's a difference in the potential at two different spots in the metal, and so electrons flow from high potential to low potential because everything goes downhill. Remember, that's actually a very important concept. Now they talk about the drift velocity. This is the movement of the electrons. Electrons do not move very fast. They say millimeters per second. That's fairly slow. But they said to compare this to like dominoes, where each domino does not move very far nor very fast, but the effect of that fall, where that one domino hits the next domino that hits the next domino, can create a massive effect down the road, very rapid down the path very rapidly. The same way with electrons, as an electron moves, it affects the next electron, which affects the next electron, which affects the next electron, either pulling or pushing, depending on how we're looking at it. Actually pulling and pushing, because an electron moves one direction, the electron next to it is being repelled, but the electron behind it, now there's a positive spot, or there's a positive spot because the electron left it, so the other electron will jump into that spot. So there's a pull on the one behind it and a push on the one in front of it. And the impulse of that happens near the speed of light. It's very fast. So the impulse of motion, like the effect of that electrical impulse, will be very fast next to the speed of light. But the actual movement of the objects is very slow. Now, in solid conductors, metals, which basically means metals, electrons usually carry the current. We've actually already said that, but just to reiterate that. Okay, the unit of current is the ampere, and this is named after a guy named Ampere. We usually say amp. An amp is defined as 1 coulomb per second. And you don't need to know this whole definition, but here you go. The constant current, which, if maintained in two straight parallel conductors of infinite length of negligible circular cross-section and placed 1 meter apart in a vacuum, would produce between these two conductors a force equal to 2 times 10 to the negative 7th newtons per meter of length. Ain't that cool? Okay, I've never heard that definition before. I just read it like I said, this came from Bob Jones, and I actually didn't read that definition. Okay, so that's the technical definition of an amp. The practical definition: 1 coulomb per second. We actually talked about a coulomb, I believe, in our static electricity chapter. It's the charge of a certain number of electrons. The direction is arbitrary. But textbook convention is that current flows from higher potential, which is a positive charge, to a lower potential, which is a negative charge. And this is really important. We talked about this in phys sci at the college, those of you who took that. Conventional current flows the opposite direction from what the electrons are flowing. And this takes us back to our chapter on static electricity and Ben Franklin's mistake, where Ben Franklin thought that the one kind of material had an excess of fluid and the other one had a less fluid, and he got it backwards. Anyway, so electrons flow from negative to positive, because negative charge means there's lots of electrons, and they're going to flow from high concentration of electrons to low concentration of electrons, or from negative to positive. But our conventional current that what every electrician would use, if you take this is actually, sometimes you guys say, when are you going to use this? You get involved in electricity, you will use this stuff, or electronics, either electricity or electronics. You will definitely use this stuff. Every current, every circuit you design, the current flows from positive, higher potential to lower potential, positive, negative. That's not what happens in reality. It doesn't really matter. It works to look at it that way. It doesn't change our math. Well, it doesn't change the results of our math any. In a direct current, the motion of charges is the motion of charges to cancel a constant direction potential difference. In other words, the potential difference is always the same direction, so the current always flows in just one direction. We're not going to talk about alternating current, which is the opposite, where it goes back and forth. We're only going to talk about direct current right now. Potential difference is the difference in electrical potential between two positions. So the difference between point A and point B is VA minus VB. The difference between point B and point A is VB minus VA. And they're always going to be opposites of each other, equal in magnitude, but opposites. If you stop and just think about it, that just makes sense, okay? So potential difference. And we don't use that a great deal. Well, we don't use that a great deal. But it is important. So if you're flowing downhill, if you think of electrons as flowing downhill, the distance downhill and the distance uphill is the same, but opposite in direction. And then therefore, the potential difference can be positive, negative, or zero. Polarity markings, positive for the higher potential, negative for the lower potential. I think that's fairly straightforward. I don't see anything fancy there. Differences in electrical potential can be produced in several ways, and I believe in your homework they ask you to give some of those ways that it can be done. And this is measured in volts, and a volt is defined as 1 joule per coulomb. Now, joule is energy, so this is how much energy you're giving per coulomb of charge. So the voltage, the potential energy, is a matter of how much energy you are giving, per unit of charge, or per coulomb of charge. So that's how much push there is, how much energy the electrons have. So the current has to do with how fast the electrons are moving. Okay, that has to do with the current. You can think of it as water current. Okay, parallel to water current is how fast the water is moving. Voltage has to do with how hard it's moving, how much energy it has. It can be traveling very fast, but be very light, or it can be very heavy or very strong. And that would be the voltage or the potential difference. 1 coulomb is defined as a total charge of a specific number of fundamental charges, which is 6.24 times 10 to the 18th electrons. And a coulomb would be 1 amp second. So amp is the speed, how fast it's moving. Multiply that by the second, and that tells you how much charge is going by, 1 coulomb per second. So an amp is a coulomb per second. A coulomb is an amp second. Basic algebra there, not a big deal. I told you to get the definition of circuit from top of page 450, and a circuit is formed if the path is closed. So if there's a closed path around which the electrons can flow, that is called a circuit. All right, we jumped to 20.6 and talked about resistance. I was trying to make it easy on you guys when you were reading through this. Every material tends to impede the flow of charge. There's some resistance to charge flowing through a material. Temperature can affect that. Okay, so the temperature is an important factor. So that's the kind of material and the temperature of the material are two factors to how much natural resistance there is to the flow of charge. Now, resistivity, and we're going to talk about two different words here, resistivity and resistance. Resistivity is the tendency to impede current, and this is a property of the material. It varies with temperature, but not dependent on its size and shape. So the resistivity is a characteristic of the material itself. It changes with temperature, so you need to know the temperature to know the resistivity. But if you know the temperature, then the resistivity of the material, it doesn't depend on its shape or size, just what is it made of. That gives you resistivity. Good conductors have lower resistivities. Superconductors have zero resistivity or next to it. And superconductors are a big field, and we're going to talk. Well, superconductors only happen in very, 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 very cold temperatures. A lot of times they put them. You have to put them in some sort of like liquid nitrogen or liquid oxygen or something like that. That's really cold, like massively cold, in order to get the superconductor get zero resistivity. However, when you get zero resistivity, you can do some interesting things with a superconductor. Now, a resistor is a circuit component designed to convert electrical potential energy to thermal energy and produce a potential difference in the process. So a resistor is designed, it's a component, and its goal is to resist the flow of electrons, which creates heat. A heater, an electric heater, the wires get really hot. That's converting electrical energy to thermal energy, electrical potential energy to thermal energy. Your toaster, an electric oven, an electric stove, a hair dryer, all of those have resistors in them that are light bulb have a resistor in them that is intended to create thermal energy. Now with the light bulb, it converts to light because things that get hot also glow, which you notice with electrical heaters, but you get less light and more heat. A light bulb, you should get more light and less heat, although obviously that's not true of LEDs, but that's true of your incandescent bulbs. This is kind of interesting. Long, thin wires with higher rho values make better resistors than short, heavy wires with low rho values. And I don't really have any explanation for that. I'm not even sure what the relevance of that is, but it's one of the things that they brought out and came up on the homework. Now, resistance is rho times L over A. Okay? L is the length of an object's current path. How long is it? And A is the cross-sectional area of the current path. So, resistance is directly proportional to the length and inversely proportional to the area, and the constant is rho, or resistivity. Rho is this P with the little tail on it. Not real obvious in this particular font, actually. I borrowed it from Bob Jones, as I say. So the resistance of an object, okay, the resistance of an object has a certain resistance, is based on the resistivity of the material. What is it made of? How long it is, because the longer the electron has to go through it, the more resistance there's going to be, divided by the area, because the bigger the wire is, or the piece of metal is, the easier it's going to be for the electrons to go through it. Again, if you think of water flowing through a pipe, the longer the pipe, the more resistance there's going to be for the water to go through it, but the larger the diameter of the pipe, the easier it's going to be for the water to go through it. So rho L over A. Okay, let's talk about Ohm's law. Now, I want you to text me Ohm's first name just because I thought it was interesting. Text me Ohm's first name when you finish this video. You can send that to me. Ohm's law is V equals IR. This is relationship between voltage, current, and resistance. Voltage, or potential difference, I is current, and R is resistance. So these are the three things that we're relating in electricity, okay? The amount of potential, the amount of potential energy-ish. It's not exactly potential energy, but ish. Potential energy-ish equals how fast the electrons are moving versus how much resistance there is to their movement. Okay, this is Ohm's law. And resistance, therefore, is measured in ohms as defined in Ohm's law. 1 ohm equals 1 volt over 1 amp, 1 volt per amp. So the amount of resistance is how much energy there is divided by how much flow there is. Okay, so if it's flowing really well, that'll get you that'll indicate low resistance. If it takes lots of energy to do it, that will indicate high resistance. Okay, so 1 ohm is defined as a volt over an amp. That is an omega. That little horseshoe shape is an omega, and that's the Greek O, so that's where it comes from. Okay, let's talk about power and work. Power is expressed in joules per second or in watts. We've done that before. A kilowatt is 1,000 watts. Now, I will mention this to you. Oh, no, I guess it's this one I want to talk about. 1 kilowatt hour. This is a unit of energy. So this is using 1 kilowatt for 1 hour. Okay? So you're using a kilowatt is 1,000 watts used for 1 hour. That's 3,600 seconds. And that gets you actually 3,600,000 joules. Now, this is what's important you can think about, and that is that you pay for electricity. If you look at your parents' electric bill, it's measured in kilowatt hours. This is how they sell you electricity. They sell you energy by the kilowatt hour. Okay, and if you look at a light bulb, now the old incandescent light bulbs, typically a typical one was a 60-watt bulb. That means a 60-watt bulb would take a long time to add up a kilowatt hour because it's only 60 versus 1,000 watts. So it would take a lot of hours. The newer LED light bulbs are more like, I haven't looked at 12, 6, and then they're really low, which means that you're not spending very much on those kinds of lights. So a kilowatt hour is how we buy electricity, but it's actually a measure of, well, a kilowatt hour is energy because it's power times time. Power times time gives you energy. All right, so important formulas for electrical power. P equals VI, potential energy times current. Okay? The power equals, potential energy, electrical potential times current. Now, if you apply Ohm's law to this, that will convert that to I squared over R, because V is IR. So then if you replace V with IR, you get I squared R. And that's called Joule's law. And then if you replace the I with V over R, which is what I would be, then you get V squared over R, and that's equation 20.6. So these are 3 ways of calculating power. The simple one is P equals VI. That's the simplest one. You can use Ohm's law to replace those and rearrange them. So those are Ohm's laws. And you had to see Joule's law there, P equals I squared R. Okay, I'll be assigning you that math probably later, probably Tuesday. I'll be